Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And we have two authors with us today. And I am super happy to have Elena Dzifc with us today. And I apologize for butchering your name. And we have Jaroslav Dudík with us today as well. Elena, Jaro, welcome.
Hi, Frank. Thank you for inviting us.
Well, thank you for agreeing to talk about your very lovely APJ supplement article. And Elena, where are you located at?
Where? Well, in Montreal now. And now Montreal, this snow and evening.
Very cool. You still have a Christmas tree up. You got your Christmas?
Yes, we still have the Christmas tree.
I like Christmas. I still have my Christmas tree lights up. So, hey, you know. And it is January 25th, 2022, as we are recording this. And Jaro, where are you located at?
So I'm now at home. I work these days from home a lot.
Mm-hmm.
It's that time of year.
Yes. And you're also in Czechoslovakia, yeah?
Yeah.
And what's your position there?
So I'm a research scientist at the Astronomical Institute.
Cool. Very good. Very nice. Okay, Elena, what do you like to do for research?
I like thermal distributions.
I like thermal distributions.
Electron. Well, no, maybe particles, yes, ions, and so on.
Or Kappa distributions or something like that.
Kappa distribution, yes. Also.
Very good. And Jaro, what do you like to do for research?
So same thing. This non-thermal distributions is something we've been working with Elena for, I think I've counted today, maybe 15 years now.
Wow.
So, but other than that, I also do a bit of solar flare analysis.
Oh, okay. Cool. Very nice. Very nice. And that is going to bring us to this very lovely APJ supplement article. And I got the wrong one. Excellent for me. Let's try that again. What's going on?
No, it's the correct one.
Sorry, people. I'll get there. This should be the article. So why am I not pulling this up? Okay. My bad, people. Okay, what we're going to do is we're going to get rid of this. Sorry for the delay, people. My bad.
I think that was the correct article.
This was the 2015er, so I'm actually just going to close that out so I don't get confused, or Zoom doesn't get confused. And finally, we have it, APJ supplement series, Kappa, a package for the synthesis of optically thin spectra for the non-Maxwellian Kappa distributions. 2, update to compatibility with CHIANTI version 10. And Elena and Jaro, take us away.
So thank you for the invitation. This paper concerns, as you said, a package for doing the spectral synthesis of optically thin spectra. This means spectra of astrophysical objects such as solar and stellar coronae. And the package is focused on doing that for non-Maxwellian distributions, meaning in situations where the electron distribution departs from the equilibrium Maxwellian.
Yes, good.
So, and this article concerns an update. Since in last few years, there have been tremendous advances in the atomic spectroscopy. There have been new calculations have been done for various rate coefficients for various processes, such as ionization, recombination in individual ions, and then transitions between excited levels within the individual ions, so excitation, de-excitation rates, and so on.
Cool.
So why do we do this? Of course, in astrophysics, if you want to learn about the nature of the emitting medium, you cannot go there directly. You only have the observed signal. And of course, the spectra has the most information on the medium.
Mm-hmm.
So we have to understand, how these various spectral lines come to be.
Good.
And then we see the equation 1, which is a sort of standard equation for a rate coefficient.
Mm-hmm.
For a particular process. And this equation tells us why we need to care about the distribution function of electrons. That's the F as a function of velocity v.
Mm-hmm.
And it is because the rate coefficient is an integral over all the particles, over the velocity distribution times the cross-section sigma.
Yes.
And times the particle velocity. So in fact, if the electrons are not Maxwellian, they are not described by, say, a simple temperature. Something has been heated, accelerated, then the nature of the emitted spectra changes in proportion to the distribution function. And of course, to calculate how the spectra looks like, you have to get the individual rate coefficients for the ionization, recombination, excitation, and so on.
Mm-hmm.
And then you can calculate the spectrum.
Cool. Good.
So maybe a bit more on the departures from the Maxwellian.
Yeah.
I mean, the general idea why we use the Maxwell distribution is that if you have a bunch of particles and you just leave them be, then by the virtue of mutual collisions, they will establish an equilibrium Maxwellian distribution at some temperature. But it turns out that the electrons, as they do the Coulomb collisions, their cross-section decreases with the square power of energy.
Uh-huh.
So in fact, the very fast electrons are progressively less collisional, which means that it takes a long time for these electrons to come to equilibrium. And in fact, if the number of collisions is low, you may never reach equilibrium. So you might be left with a sort of high energy tail, which we will talk about as we come to the Kappa distributions.
Great.
So a bit more formal argument would be regarding the electron Knudsen number, which, as we say in the paper, is the ratio of the electron mean free path to the pressure scale height or scale length in the medium. And if the electron mean free path is, say, significantly large, say more than 1% of the pressure scale length, you will never reach Maxwellian.
Fair enough. Yep. Mm-hmm.
So, instead, you might end up with something as is shown on figure 1, namely something that resembles a Kappa distribution. And we are showing the Kappa distribution in various colors here. The black is the Maxwellian, and with increasing energy, the x-axis is plotted in logarithms. So as the electron energy increases, the Maxwell decreases strongly.
Right.
And contrary to that, if you have these high energy tails, say due to electron acceleration by any heating processes such as reconnection, wave-particle interactions, or turbulence, you end up with these high-energy tails, which have much more particles in the tail at energies of, say, a few keV.
Uh-huh.
So these are in fact power law tails. So the distribution decreases as some power of the energy. And the power is related here to the Kappa index.
Mm-hmm. Good. Yep, I'm with you.
So maybe we talk a little bit about the relation of the Kappa distributions to Maxwellian. So if you can find the equation 2, that's on the left column somewhere. So this is the mathematical formula for a Kappa distribution. And what can be seen is that as the Kappa goes into infinity, you recover the Maxwellian exact. So a Maxwellian is in fact the limiting case of a Kappa distribution. And then the other limit is where Kappa is equal to 3/2, where the entire distribution basically switches to a power law. Yeah, and then between these values, you have a sort of peak, which then smoothly goes to the high energy tail.
Okay, cool. I'm with you.
And of course, in recent years, there have been various definitions of the Kappa distribution in literature. So, with respect to the works of Marian Lazar et al., our definition corresponds to a sort of something that was dubbed the Kappa A, and that. Because the Kappa is not the only parameter of the distribution, you also have the T, or the temperature. You have to make a choice whether you will select temperature as the other independent parameter, or whether your independent parameter will be the mean velocity theta, which is shown here in the equation 4, which is visible in the lower left corner.
Yes.
So, I mean, in spectroscopy, we care about temperature because temperature is related directly to the energy of the system. So if you have a temperature, the energy of the kinetic energy of the particles is, of course, 3/2 times the Boltzmann constant times the temperature. And traditionally, if you assume Maxwellian, then temperature is something you need to measure.
Yes.
And, a lot of people understand the temperature. We used to say, that the solar corona has a few million Kelvin, and in solar flares you have maybe 10, 20 million. So just to have this seamless transition from non-equilibrium to equilibrium, we choose the temperature to be the independent one.
Okay, fair enough. Yep.
And so of course the electron distribution, if you have strong heating, reconnection, and so on happening in the corona, the real electron distribution can be strongly model dependent, can be evolving in time, but then you need modeling of particular processes to understand what happens in the corona. We work in the other way. We work in the way that we have the observed spectrum, and we want to understand, whether there are any accelerated particles.
Okay.
And of course, if you analyze the spectrum, I mentioned that you need to determine the temperature. You need to determine other parameters such as electron density, and then we would like to know, as mentioned, that whether there are accelerated particles. So it would be nice if we could do it with the introduction of only one extra parameter.
Okay.
And that's why we chose the Kappa distributions, because that has both the high energy tail and only one additional parameter.
Yep. Very cool. Good. So,
and then of course the task is, if you want to do the modeling of the spectrum, is we go to the synthetic spectra. We want to calculate the synthetic intensities, which are given by the equation 5.
Mm-hmm.
And here the important bit is that we assume the emitting medium to be optically thin. meaning everything that is emitted along your line of sight, along various places in the corona, gets to you without being absorbed in the medium. So you just count all the emissions, meaning you do an integral over the number of emitters, which are hidden in this, in the line contribution function G, and then times the square density in the medium.
Yes.
And the line contribution function is a fairly standard stuff. Contains the energy of one electron, that's the hc over the lambda in a particular spectral line, times the probability something is emitted by the Einstein coefficient. And then you have these two fractions. The first fraction is if you have an emitting ion X of an element X in the ionization state plus M. So say it lost M electrons and this ion is excited to some upper level J. Then this fraction is the fraction of the excited ions, or the number of emitters with respect to the total number of the ion plus M, and then we normalize with respect to the particular element X.
Yes.
So you need to calculate the excitation fraction and the ionization fraction. Yep. And typically this is done in the coronal approximation, which means that the timescales that govern the excitation and ionization and recombination are so different that you can treat the two separately.
Got it.
So yeah, your ionization composition is independent from the number of ions in some excited upper state J.
Okay.
And of course, it's not always true, and there have been improvements to the way spectroscopy is done by inclusion of ionization and recombination to and from excited levels in the past few years. And our modeling is based on something called the CHIANTI database, which is a huge and publicly available atomic database and software. I think it has a few hundred ions in it, and for each ion you have maybe hundreds or in case of iron even thousands of excited energy levels.
Yep.
And you need to calculate all the transitions from between each excited levels. And of course, if you have 1,000 excited levels, then you have almost 1,000 factorial of individual transitions. So the calculations quickly become extensive.
Yes.
And CHIANTI CHIANTI does all this for the Maxwellian. And the Kappa builds on CHIANTI, so it's written in the same IDL software, but does it for the Kappa distributions.
Okay. Cool.
So as I said, there have been updates to all these ionization, recombination, and excitation rates. So we have to reflect that in the new Kappa to be compatible with the latest version 10 of CHIANTI. And if you can go to the next image, which is showing at the bottom. So here we show behavior of relative ion abundances with temperature as a function of Kappa. So in the solar transition region between the chromosphere and the corona, we have some ions as the oxygen 4, that's the one on the left.
Yes.
And you can see if you add high energy electrons, the situation changes here dramatically, because for Maxwellian, that's the black line. The ion is typically formed at temperatures of about 100,000, meaning log T 5 to 5.2. Yeah. And as we add particles to the high energy tail, meaning we go towards the lower kappa values, this ion gets formed in progressively lower temperatures.
Yes.
And I think this behavior has been shown first time by Elena in 2013, that this is fairly typical of transition region ions.
And what's the difference between the solid and dashed lines?
Elena will correct me if I say wrong. I think the solid line is the previous the dashed lines are the previous calculations.
Yes.
Okay, cool.
And the full lines are the new calculations.
Very good.
So, the oxygen 4 is an example where not much has changed.
Yeah.
If we go a bit to the right, this is a fairly typical ion of the solar corona. That's the iron 13, which is formed at a few million degrees, say at log T 6.2.
Yep.
And here we have some differences since I think it was the dielectron recombination rate for iron 8 that changed. Do I remember correctly, Elena?
Yes.
Since in this temperature region there are many overlapping ions, you can at one particular temperature you can have emission from many iron ions. Then a change in one rate has a knockoff effect on the neighboring ions. So even iron 8 and iron 13 are different. They differ by 5 electrons. And if you change one, there's still changes in the iron 13. So we had to, obviously we had to
they're coupled.
And then the last image, this is a flare ion is the iron 21, which is typically observed by instruments such as IRIS, or the atmospheric imaging assembly on board the Solar Dynamics Observatory. So this is a fairly standard flare ion. And what happens here is for the Kappa distributions, actually the ion is formed at temperatures that are not 10 to 7, but are formed at log T 7.3 or 7.4. So, at temperatures of not 10 million, but say 20 million.
Okay. Very good. Cool. I'm with you.
So can we go back to the text? One of the improvements in CHIANTI has been that of course, the ionization and recombination, they don't only happen from the ground level. They can only happen from the excited levels. So we had to take this into account. And as we say, we provide machine readable files for the level resolved total ionization and recombination files. The .tioniz_r and .trecomb_r files.
And where does somebody get these? Are these on like Zenodo or some other database somewhere?
So typically you get these for Maxwellian within CHIANTI, which is freely available.
Right.
And for Kappa, they are also freely available. You can get it at the website of the Kappa database, which is hosted at our institute.
Cool. Good. Thank you.
And I think maybe Elena can tell you how these level resolved rates are calculated.
I see next figure maybe.
Next figure.
Yes.
There you go.
What is here?
This is a comparison of the level resolved radiative recombos.
Oh, yes. Because typically we don't have a cross-section for radiative recombination or ionization, we need to use the approximation for the radiative recombination rates. It is typically power law approximation, and we can also calculate these rates for Kappa distribution using approximation of Kappa distribution by sum of Maxwellians. This is method by Hahn and Savin. I don't remember maybe 2015.
Yeah, 2015.
2015, yes.
Yeah.
And we compare results for the calculation by using power law approximation with calculation by Hahn and Savin. These points are
Okay.
this for different different ions, C4 maybe this the other,
Yeah.
but you can see that they agree very good.
Yeah.
And we can use any approximation what we want. So this is for radiative recombination. For the electronic recombination, it is possible to use parametrized form. It is from, for example, also from paper 1 and from my paper from 1990. Yes.
Okay.
A very, very old paper.
Definitely.
And so, but of course, also for the ionization, next figure, please. Also for the ionization, this is approximation. This is approximation for the electronic recombination equation. This one. So for the calculation of the level resolved ionization rate, because we don't have cross sections, we need to use method by Hahn and Savin, and we need to calculate the ionization rates using this method. Problem from CHIANTI is that this 1, 2, 3, 4, 5, 6, 7 points is everything what we have in CHIANTI for the ionization rates for Maxwellian distributions.
Okay.
And
I think for Maxwellian that is enough, but you know.
Yes, this is enough.
For Kappa distributions,
if we want use the approximation, we need to have the rates for many temperature outside of this temperature interval.
Yes.
So we need to extrapolate these rates. This is it is not problem for the lower temperatures. This is exponential increase, but in this part we need to approximation by exponential integral. Yes, for this part. The precision is not high, because if we need the other extrapolation, we can have the other values of the ionization rates. But in sum of Maxwellians, we need to multiply this contribution from this temperature by very small number. So the final error is not so big. It is about I don't know, 10, 15%. So it is okay.
Okay. Good.
So, yeah.
And since we started talking about these approximations, for the excitation and de-excitation rates, which is the other ratio we need to calculate the intensity, only the rate coefficients are available. We don't have the cross sections. And if you remember at the very beginning, we were talking that we need to integrate over the cross section multiplied by the distribution function to get the rate.
Right.
So Elena devised in the past quite an ingenious method how to reverse engineer the cross section from the rate.
Okay.
And in the first paper where we first created the Kappa database back in 2015, we did extensive comparisons for few cases where we actually had the cross section from from the atomic data calculations.
Got it.
With the reverse engineering method, and typically we get a precision of about within 5%, which is comparable to the precision of the atomic data themselves. So, that's quite good. We are not introducing any error by reverse engineering Maxwellian rates to cross sections.
And I think that's figure 3 in the 2015
Yeah.
paper.
Yes.
Let's go ahead and take a peek at that. So I'm going to stop the share here. Hopefully I don't get too messed up. And all right, let's blow this up. Figure 3. Okay, let's see what happens. All it can do is mess up. Let's see, that's the 2021 paper. This is there we go. This is a 2015 paper.
Yeah. Go back to the figure.
I just wanted to get the title up so people know it.
Right.
And figure 3, there we go.
So in the left panel, you can see the triangles are the rate coefficients for a particular temperatures as available from CHIANTI.
Yeah.
Then the red line is the approximation with some appropriately chosen function.
Very nice.
And then in the middle panel, the omega, the black spiky line, is the original non-dimensionalized cross section.
Okay.
And the red line is our approximation. And just remember, we are integrating over it. So, the contribution of the individual spikes in the overall integral through the energy is quite small.
Right.
And if you do the integration, then we go to the right panel, where we have, again, the rate. And we are comparing here by triangles the direct calculation from from the cross section with all the resonances, with all the spikes, and excuse me, by the full lines we see the rate obtained by the approximation. You can see that they agree very well, typically within. And the way we need to do this is because, of course, there are hundreds of astrophysically relevant ions, and each of them has many energy levels, and transitions between all the levels are very high. They're I think in the tens of millions, and it's not something you can check one by one. So, you need to do these approximations for all of them.
I'm with you. Yep.
And then where we could, we did this kind of comparisons, and generally the precision is 5%. So
Good. Okay.
Okay. I think we can go to the current paper.
Yes. Let me make sure I don't confuse myself again. And there we go. This is where we left off.
And I think we can go to the table in the next page.
Ooh, very nice. Wow, look at this. Very cool. Okay. Okay.
So this is just a list of routines that we modified to do all sorts of calculations. I would.
You ever wanted to know?
Yeah, I would point out the first one, the Kappa Pro, which is an interactive widget for calculating spectra for the Kappa distributions. And then, you know, the users of CHIANTI will know all these other routines which are suited for various types of calculations. The CH synthetic calculates line intensities as a function of temperature and density and so on. Then you have the MISCalc, which calculates various quantities. And there are also routines that read or calculate the total recombination or ionization rates. Yeah, and also the contributions of continuum.
Cool. I have a question. So if I have a given temperature and I want to calculate a spectra using Kappa.Pro, is this something that runs in less than 1 second, in a minute, in an hour, 10 days? What is this?
Depends on how large a spectrum you want. If you want, say, a few angstroms or tens of angstroms, say a limited spectral range, you will have your result within maybe 2 minutes.
Okay.
If you want to have the full extreme ultraviolet and ultraviolet spectrum for a range of temperatures and densities, then the calculation might take a few days.
Okay, very good. Thank you. I'm with you.
Okay, and I think we can go to the various applications. So, of course, we looked at the behavior of spectral lines, and so these are various spectral line intensity ratios. So you take intensities of 2 lines, yeah, you calculate a ratio, and some of these ratios are sensitive to temperature, some are sensitive to density, such as these ones shown in figure 6, and others are sensitive to kappa. So we try to estimate these parameters of plasma. And these ratios shown in figure 6 are all fairly well known for determination of electron density. So such as the iron 12, 186 to 192, that's the top left one.
Yes.
And we are showing this ratio for the Maxwellian in black and for Kappa 5 and 2 in green and red. And the nice thing here is that the ratio doesn't change much with Kappa, and there are only very minute changes. So this ratio is one of the best diagnostics of electron density in the solar corona that we use.
Yep.
And this also means that you can use this ratio to get an estimate on electron density independently of temperature, which is shown by these different line styles, and kappa, which is shown by the different colors.
Yes.
And of course, we also want to measure the temperature and the kappa. So which we come back to the ultimate goal is are there accelerated electrons in the solar corona? If you can go to the figure 7, so you can you can measure the temperatures and kappa if you find the appropriate lines sensitive to the non-Maxwellians. And yes, one of the main applications of this database, at least for us, is to find new diagnostics for these accelerated electrons.
Okay.
And here we show an example of such a diagnostic. I think Elena went through various lines of oxygen 3, 4, and 5, and found that at the lines at around 500 angstroms, with respect to the lines at 700 angstroms.
Got it. Yeah. I see.
These are sensitive to temperature,
Okay.
which is shown by these various triangles. But if you combine it with a different ratio of oxygen free, the one on the x-axis, the 507 with respect to 525 angstrom, you get also something that is sensitive to Kappa distribution.
Oh, cool. Okay.
So, if you have, say, a Kappa 2, this ratio for one temperature should be 8 and not, say, 2 as for Maxwellian. So this is quite a large sensitivity, which
yes,
yeah,
yes,
which will allow us in the future, hopefully, to determine these Kappa distributions.
Oh, very nice. Cool. Cool. Good. Okay, I'm with you.
And of course, as there are many mission lines from various ions, we try to look for other diagnostics. So the last figure here is, it's the figure 8. And this is the spectrum for iron 14 that goes from the extreme ultraviolet to, say, around 200 angstroms in the left part. To that's the extreme ultraviolet. Then you go to the ultraviolet, and then you have this forbidden green line, which is in the visible.
Okay.
And one thing that we learned is that this forbidden line behaves a bit differently to these extreme ultraviolet lines, in a sense that if you fix the temperature and you change the Kappa distribution, the EUV lines, they change from the Maxwellian, the black, to they decrease if the Kappa is 2. That's the red spectrum.
Yes.
But this forbidden line decreases, but by not so much.
Oh,
so the ratio of this line to the EUV lines changes by 50% compared to Maxwellian. So, which is also another potential diagnostic.
Correct. Yep. Cool. Very nice. Very nice.
And I think that's it.
Okay. Very cool. We got a summary. Here's a website, people. If you want to go ahead and grab this, go out and get it. And have some great Kappa fun. Very cool. All right. Elena, Jaro, thank you so much for walking us through your very lovely article on Kappa. So you touched on it a little bit during parts, but I want to bear in a little bit. Where do we go with this work over, let's say, the next 2 to 5 years? Is there laboratory astrophysics measurements that could be done? I was somewhat shocked to hear that a lot of those cross sections are not measured. So is there laboratory astrophysics? Is there, are there plans to do, a paper 3 in this series with Kappa? Will there be a CHIANTI 20? And just sort of where do we go in the future?
Me, I would like to calculate non-stationary spectra.
Okay.
With impulsive non-equilibrium Kappa distribution, and calculate the effects, and if the effects is possible to measure or see by UV spectrographs. So it's mine research.
Okay.
In future.
Very cool.
Yeah, and for me, the immediate task, which means for the next few years, is to measure these Kappa distributions from as many instruments as possible. Of course, we have a few satellites in orbit, such as the Hinode, which has an eye spectrometer. Then there's IRIS. There's also SPICE on board Solar Orbiter, and there will be future instruments on board the Solar Sea. And they provide us with some options to measure these Kappa distributions. So I will be working on determination of the Kappa in the solar corona as precisely as possible. you know, it goes back to this old coronal heating problem. We don't know how the corona is heated, and if we get a constraint on the number of accelerated particles, then
Yes.
you know that.
Yes.
Yeah, that's an important piece of the puzzle.
Definitely. Definitely. It gives you a sense of, you know, is it magnetic reconnection? Is it something else? Yeah. Very cool.
There's also been a NASA rocket in the X-rays, which observed multiple lines of iron 17 and 18, which are also sensitive to non-Maxwellians. So that's my next project.
Very cool. Very nice. All right. Elena, Jaro, thank you once again. And that will do. And I hope this made your astronomy day just a little bit better, everyone. And we will see you on the next one. Bye-bye.
Thank you. Bye.
Bye.